So what is stream warehousing? I'm going to take kind of two opposing views here. You might have heard of things called data stream management systems. So to take an extreme view of it, what you want to do is you want to do fast processing main memory as a stream of data flows past you. And typically you use small data windows. You're aggregating things by, say, 5-minute buckets, doing very, very time-constrained joins, and maybe hitting some metadata tables. But basically, you're dealing with small data windows and main memory doing one-pass processing. The main thing that you want to do in a data stream management system is data reduction and alerting, roughly speaking. On a totally opposite pole is a traditional notion of a data warehouse. And in a data warehouse, you're doing long-term data storage. And you have these curated data sets. If you want to know what the company thinks is the truth of some matter, you go to the data warehouse. And one important property of a data warehouse is you're going to fuse data. You have the ability to fuse data from many, many different sources. So you might have hundreds or thousands of feeds of different views of different entities going into this data warehouse. And because of that, you can create some very complex and sophisticated derived data products and run some complex analytics on it. So a data stream warehouse is supposed to fuse the two, which means that I'm trying to build a data warehouse that has continual near real-time updates. And so the idea is somewhere in the cloud, somebody's sending me a bunch of data feeds, and they're sending me these data packages. And when a new data package comes in, I'm going to put into what's called a base table. It's just a table view of whatever records are coming in these packages. These packages might arrive once a minute, might arrive once a day. There's a high variability. And from these base tables, we might want to derive some more sophisticated data products. And you might want to do this for a number of reasons. So this is an example from the Dark Star warehouse. There's a data feed right here. This is actually reporting the bytes per second transmitted over each core network interface link. And in order to make use of this information, we need to associate it with a lot of metadata. And so here's one form of metadata we're grabbing. Here's another. We have to do a lot of fairly non-trivial processing on it. And eventually, we join it into a fused data set over here. The reason why this is important is that just because you knew that this particular link was transmitting on average 900 megabits a second doesn't really tell you very much. What you need to know is, well, is this a 1 gig ETH link or a 10 gig ETH link? And that makes a big difference. We also collect a lot of other data products. We might collect the number of distinct interfaces we see. This we use to raise data quality alerts. And then we might aggregate per hour and per day to get longer term information. So we're doing a lot of, in some sense, ETL within the warehouse itself. And since it's within the warehouse, all the data flow, all the processing is completely automated. Data comes in, it just chunks on in. This is a more complex application. There's quite a lot of different data sources. There's some very complex logic going on here. This is an alerting application. We're looking at some active measurements. If the active measurements are bad for too long, we raise an alert that a certain link is having a problem. One of the reasons why this is such a complicated application is it requires sequential processing. SQL is terrible at sequential processing. We put in a new language module which handles sequential processing well, and we greatly simplified this. There's a paper about this in passive and active monitoring this year with Jennifer Yates, Shubho Sen, myself, and Lukasz Golub. So this is what the system kind of looks like. So let me talk about some applications of it. The application, there's a number of applications of the software I've written. The easiest one to talk about, because I work right next to these people, is something called Dark Star, which is a big data warehouse within AT&T Research. And the goal of Dark Star was to collect diverse and large-scale data feeds from various kinds of network and other elements and put them all in one place for analysts to use. And you might recall in the first talk from yesterday, DJ Patil was talking about how to be a data ninja or something like that. And he had two important points, one of which is you need to do data fusion. Your product's much more interesting the more data you can put into it from different sources. And second, if it's easy to do, people will do it. So we want to put all the data into a warehouse so an analyst can come along and very rapidly prototype something and just make it easy for people. So a fair chunk of the network research that comes out of AT&T research these days is based on data coming out of DarkStar. We also do a fair amount of data mining for the company itself, and also as research. For example, to correlate network events with network failures. What in a network can predict a future failure? If we can establish that, and we look at, this is a big project, it's called the Generic Root Cause Analysis project. It tries to look at hundreds of different predictors. And if we can do that, we can start writing some alerting applications, predictive alerting applications. When we raise the alert, then we're going to have to start doing some troubleshooting. And all of this we're going to be doing from this combined real-time and historical warehouse that contains all these different data elements. And it is, one thing I have to point out is that the network is a very large and complex system. It's not just IPv4. AT&T runs actually MPLS network with lots of stuff flowing over it. So does everybody else. I'm going to talk about two projects in particular. One is called Argus. This is done by Hee Yan and Jiwei Gi. And the other one is Ptolemy by Jiwei Gi again, Don Caldwell, and Bill Beckett. The good thing is I didn't have to actually write these applications. So this is a slide which, it's kind of a standard slide which gets shown at these things. It tries to talk about the diversity of data elements which go into DarkStar. Depending upon what they're talking about, you might see different elements coming in here. There's actually more flowing into the network than just what you're seeing here. But you can see things like, for example, NetFlow. So if somebody's doing network data mining, they're always saying, well, we grab this NetFlow feed. The problem is you actually need a lot more stuff to make your NetFlow intelligible. For one, we need configuration feeds. The configuration feeds are that metadata. It changes every day. Our network is not completely static. It's the metadata that helps us interpret all the other elements that we're getting. SNMP polling tells us, for example, how many bytes per second are flowing over a link. There's a fair amount of deep packet inspection, which gives us very detailed measurements about what's going on in the network. Customer feedback, routing information, how the routing algorithms are running, and some active measurements and other stuff I don't understand. So Argus is about detecting service issues specifically in the mobility network. So a couple of years ago, AT&T people decided that we needed to better address AT&T's quality of service in AT&T's mobile network. Based on the work we've done in DarkStar to improve our core network, research became the focal point of a data-driven, developing data-driven applications to improve our mobile network. And one of the results is Argus. And what we're going to be doing is we're going to be looking at performance measurements from a deep packet inspection tool called a GS tool. This used to be called Gigascope. This is a project I worked on a few years ago. It's relatively mature now. And we want to collect things like TCP retransmission rates, round trip times, throughput, and we want to plot them and then look for anomalies. So this is TCP retransmission times. This covers about a 2-day period. And over here, it's retransmission times are spiking. Retransmission rates are spiking. This indicates that a sudden problem has occurred on this link, or whatever the end-to-end thing is we're measuring. What's the impact? We've gone from reducing the time it takes us to detect problems from days. If you're not looking at the data, you can't find these things, to about 15 minutes. And we can do things which are actionable. Now this Argus is interesting because it involves some spatial localization, which I'll talk about in a minute, and also things like time of day and location information, because this value might not raise an alert if you didn't have the context of this history. And this, again, is one of the reasons why you need both real-time information and long-term information in your warehouse. This is something about mobility localization. I don't really understand how the mobile network works, but mainly the idea is you have these cell sites. Those are those weird little antennas. They're connected to a radio network controller. Those things are connected to a serving GPRS support node. GPRS stands for General Packet Radio Service. That's the limit of my knowledge. Anyway, if a number of sites connected to the same RNC are having a problem, you might determine that the RNC is having an issue. If it's bigger than that, you might detect that the SGSN is having an issue, and so on and so forth. So locality information is very important in trying to interpret the data that you're getting. This, by the way, is another metadata feed. It changes, though slowly. You have to keep refreshing it in order to properly interpret the data that you have. And you have to keep a history of it if you want to do long-term data mining. So this is a nice little example. I didn't do this work. I just grabbed these slides. What's happening is we're seeing these TCP retransmission spikes. That's indicating something bad's happening. This says we're getting a spike over here. This says other nearby cell sites are also experiencing problems. This suggests that it's not a problem within the site itself. It's a problem in the RNC, the SGSN, or whatever. Then you start doing troubleshooting. You have to go look at other data products. So this is C utilization flattening. I don't know exactly what that is, but basically you can kind of see this thing's flattening out over here. You're not forming a proper peak. That's suggesting that you're getting rate limiting somewhere which you're not expecting to get the rate limiting from. And then the root cause is something really weird, which you're not going to find in the manual. It winds up being the case that for the particular 1 gig-ETH card that they're using, which is 48 ports, these 48 ports are divided into sets of 8 gig-ETH ports, and each set of 8 gig-ETH ports is limited to 1 gig total transmission rate. Yeah. So it'd be nice if they told us that to begin with, but now we know. And this, by the way, is very, very common. You have to do a lot of troubleshooting in order to detect these sorts of things. So you really need to look at as many data products as possible and correlate them all together in order to properly understand what's going on in your network. But you might want to look at more than just data from the GS tool. This, by the way, is kind of showing that you might raise alerts even though your round trip times are kind of within normal levels, but compared to what you would expect for this time period, they're a little bit spiking. We can look at other sources of data to raise alerts. We can look at call drop rates. That's more mobile telephony-oriented kind of a data feed. We can look at customer mobility tickets. If people really start complaining more than average, maybe something's going on. And of course, some people would rather complain on Twitter than call up and complain to AT&T. So we actually load, there's been a project to mine Twitter for actual information about my service and such is really awful, and try to monitor it and try to see if we're seeing spikes in that. This, by the way, does get fed into Darkstar and is part of the total set of data products that you can use. Another example is, another tool is something called Ptolemy, and this provides a at-a-glance, top-down view of what's happening in our network. And I don't pretend to totally understand what's going on here, except that green means link is good, red, I guess over here, means link is bad. There's various kinds of drill down you can use. People like to look at this to get comfortable or uncomfortable with what's happening. There is something interesting that occurred last year, well, tragic. Namely the Japanese earthquake. And in the GNOC, they're looking at this Ptolemy tool, and they're able to, I'm told, they're able to tell that something strange happened in Japan before they heard the news reports because all sorts of links started going out. So you see all these red links coming out of Tokyo. And we're also able to go back and take a look at how the network is responding to these problems, and it's doing a fair amount of automatic traffic shifting. So there's two interesting things. One is in real time, you can tell that something strange is happening to the network. And number two, people like to replay this to see just how did, we have the history, so we have a replay facility, just how did the network respond to this kind of a large-scale bad event. So that's the, I don't work on actually developing the analyses. I work on developing the data system underneath it. The particular project I've been working on for the last few years to support this is something called Data Depot. It kind of started small. The GS tool is producing huge amounts of data. We had to put it somewhere, so I was producing it all the time. So it kind of got this temporal feel and all that stuff. And then it just kind of blew out of all proportion and took over my life. So it's a data warehousing system developed for stream warehousing. It's designed to be, at least the ideas are pretty much independent of the underlying data warehouse. There's a few things I assume. I assume that I have access to some kind of multi-version concurrency control. And what Data Depot is really all about is a technology for pushing updates to receiving all the time through your database, through all parts of your database. And again, I have slides for three things: update propagation, temporal consistency, and some real-time scheduling stuff. I'm probably not going to get to it. I'm going to try to focus on notions of consistency in this kind of a system. And this, by the way, is some work that I did with Łukasz Golab and Władysław Szkapniuk. So what happens in Stream Warehouse? Well, you get all this raw data coming in, and when something new comes in, you try to put it somewhere. Usually, the way that you want to run a warehouse like this is you want to do partitioning. You want to do some sort of temporal partitioning. So when new data comes in, it's probably newer than all the previous data, so you just create a new partition to hold it. That's nice. And then you push these updates into the higher level data products. If you have a really big table, you might use additional dimensions of partitioning, but we're always going to have a base level of partitioning is somehow temporal. So in order to be efficient about these updates, and by the way, since I'm using multi-version concurrency control, I'm always recomputing the updates in total. There's some other tricks you can play, but I'm always recomputing any affected partition. The thing that we want to do is we only want to propagate the increment. So if I see this thing has this base table has some new data here, and this base table has some new data here, I want to update, and I have these partition dependencies, I think like 5-minute buckets or 1-minute buckets or something. And this table is a join of these two. I only want to recompute these two particular partitions. So I might recompute 10 minutes of the 2-year history. That's pretty efficient. The problem becomes, how can you determine if a source partition has more recent data? So when I first started, I was just hacking around. I figured, last update timestamp. That's an easy thing to look at. That's how make works. So obviously that's going to work. It turns out that make doesn't work. There's the interest of time. I'm not going to go through the example, but make doesn't work. So I had to go back. I had to think about what it means to propagate updates. Because if we want to build these complicated applications, I want to have some assurance that all updates actually get propagated. And you're not doing too much extra work, or no extra work at all, ideally. And I'm aiming for something which is called eventual consistency. If there are no more updates to my warehouse and my scheduler did reasonable things, then eventually every update gets pushed through. We came up with the second version, which is a small modification of what we had. This used something which is the equivalent of read-write locks in terms of the updates. This led to lousy real-time response, and I'll show you what I mean in a second. Try it again. We came up with another version that doesn't have any scheduling restrictions at all. Remember using multi-version concurrency control so that I can do reads and writes at the same time, different versions. It uses a small amount of additional metadata on a per partition basis. This is important because we have thousands or millions of partitions in our system, and we don't want to overburden it. You do need some sort of strong consistency on your metadata management. It uses a technique which is similar to a vector timestamp. In distributed computing, vector timestamps carry dependency information. And this is a paper in SSDBM 2011. This is the effective scheduling restrictions. This is some information that we need to have in real time. But every now and then, we were computing these 60-minute aggregates, which would cause a spike in the response time because it took, for some reason, 20 minutes to compute this aggregate. That's not good. So we had to go and implement a better algorithm which does not have these scheduling restrictions. We can do updates of a table and its dependent tables at the same time, and we got rid of these spikes. So this is all good. I have eventual consistency. I might update a table while source is being updated, so there's something weird going on there. How do I really resolve notions of, do I really have the most recent data possible? That's the next issue that we have to address in a stream warehouse. So the traditional notion of consistency in a database is you have a snapshot. So you took a picture, this is exactly what's happening. Okay. But in a big complex system, you can never take a now snapshot. for pretty much the same reason that you can never count exactly what's the population of the United States. It's just changing under your feet. What you can usually do is that in most cases, you can eventually reach a point where you're reasonably confident about what the state of the system was in the recent past. So if you are dealing with large, complex systems, you have to be comfortable with a bit of ambiguity. You try to minimize the ambiguity, but you have to be comfortable with it and build systems which can deal with ambiguity. And the material I'm going to talk about was in CIDR 2011. So the idea is that why is there all this ambiguity? One reason is that data arrives in a smear over time. So usually when we get a data package, it doesn't fill up an entire partition. It might fill up just a part of it. And then because of that, we often get late arriving data. So the next data package might or might not fill up the preceding partition. And then sometimes you get really late arriving data, like an hour late, a day late, a week late. It sounds strange, but believe me, it happens all the time in every monitoring application that people are willing to talk to me about. It shouldn't happen, but it does, and you have to deal with it. So this is the number of data windows per package, per arrival of a chunk of records. These windows are small, they're 1-minute windows, but each package should provide data for just 1 minute, ideally. But this thing's like peaking at 12 different windows per package. Now, one issue here is that there's a lot of malformed timestamps within this data, and we have to send emails to people telling them to turn on NTP on their various collection mechanisms and so forth. But so this is a worst case, but this is very common. There's another reason for the ambiguity, another complication here, and that's that, remember, the reason why we have this data warehouse is that we're very interested in data fusion. We want to combine lots and lots of different data sources gathered from completely different places and put them all in one central storage place, at least logically central, so that people can run analyses on them. But here's one example which is actually real. We wanted to correlate, we had two sets of measurements. One, active measurements, which are collecting packet loss rate between 2 points. They're just two computers sending messages back and forth. And the other one is SNMP measurements collecting, for example, CPU and memory utilization, because we've determined that a high CPU utilization at a router is correlated with packet drops. So we want to, if we can join these two, and we can say, well, we're getting a lot of packet drops, and by the way, it's because the CPU utilization is high, that's a very informative message. The problem is that these two different feeds are collected by very different mechanisms that actually have two different time lags. The active measurements have a time lag of about 45 minutes on average, SNMP of about 15 minutes on average. This is not due to my system. This is how long it takes for the data to arrive, which is something I'll try to address later. And by the way, Darkstar has had 100 data feeds, 100 tables in December 2010. This is before the mobility effort, so it's about double that now. So then you have to ask, again, what do I mean by consistency? And one way to define consistency is something which I call query stability. And the idea is, how do I know that this data in this table, either in a base table or in a derived table, which correlates data from these two sources, how do I know when it's stable enough to query? Well, that really depends upon the nature of the table and the nature of your query, because if you're doing long-term data mining, you want to say, well, the data will never change, so you don't have to go and recompute my results. If you're doing certain kinds of troubleshooting, you might say, well, the data won't change that much. Or if you're doing alerting or other kinds of troubleshooting, you'll say, I'll take whatever is there. And depending upon what you want to do, depending upon the query and a variety of other things, the meaning of stable is this might be fine or this might be necessary. When you're doing data fusion, you usually do a lot of outer joins, by the way. So living in these two regions is actually quite meaningful. So what we can do is we can define consistency levels. Consistency levels are akin to punctuations. Punctuations are an idea from the data stream management field, where every now and again your data source is going to say, all the data from this point has arrived, all the data from this point has arrived. We don't really get that. We have to infer it because we don't really have this firm, full control over the system. So, in fact, the vagueness of real life means that all these things are best guesses. They're all inferences. So I'm going to talk about running examples have three very simple types of consistency. Open means there's some data there. Close means the data will never change. Complete means the data will never change. Oh, and by the way, all the data that could have arrived has arrived. If we have a lot of control over the data source, this happens in a lot of the DPI applications, we might know that we expect 4 files to comprise all the data set for this 5-minute period. If we only get 3, the data is not complete. If we get 4, we know the data is complete and closed. And these actually form a hierarchy. Complete implies closed, closed implies open. Closed is, of course, a guess. So you might have different kinds of closed. It's weakly closed, it's strongly closed. And again, what we're going to do is we're going to try to infer this at the base table. There's a variety of inference rules. If it's more than 10 minutes past, it's closed. You might say something like that. But it's a very hazy notion. But then we want to push this further up the system. A simple rule for this kind of inference is you're open if if both your data sources are open, if both your sources are open, you're closed or they're both closed, and so on and so forth. This is a very simple, perhaps simplistic rule. If you're doing outer joins, you might have weaker rules. You might, if you know the properties of the defining query, you might change the meanings of how you're doing this sort of inference. But a very simple rule is if all your parent partitions, all your source partitions have a property, then you have that property also. Then we can then that plus eventual consistency means that these notations eventually get pushed through, and that's how you know when it's safe to query the system. And it turns out that you can use this information in a backward setting also. And I'm running out of time, so let me just say that sometimes you might get, say, per day usage summaries. And you don't really want to keep recomputing that as you get every 5-minute data update throughout the day. So you might want to require that all your source partitions are closed before you compute your per day summary. And there's some tricks you can play. The problem is you don't want to have to label each table. You might just label some important tables and then do some inference as to the update consistency of the source tables. So, but this is kind of an ad hoc optimization that many warehouses run, but this is a way to automate it and make it principled. Scheduling is important. I'm running out of time, so I'm not really going to talk about it. There's some very interesting real-time scheduling issues that happen here. And one of the big things is that you can't discard updates, although you can buffer them, which is different than the usual real-time scheduling notion. So let me jump to the conclusions. You need to do this stuff in to maintain the health and improve the performance of any large-scale system. I've developed some tools for it, which I've hoped to convey. The next steps, we're trying to move to something more like a cloud infrastructure. In particular, it's really shocking that it takes 45 minutes to move some of this data to us. There's a new fairly large-scale effort to overhaul AT&T's data movement infrastructure, which some colleagues of mine are working on. So that's it.